Okay, so last class we worked through examples to find the confidence intervals for the population mean when the standard deviation was known. In practice, this assumption is not very realistic. Like, think about it. Why would we be doing all of this sample research if, like, we know the population standard deviation? We already know the population information. That doesn't make any sense. So, since the variance describes variability about the mean, obviously, like that's the whole point of it, if the population variance is known, then the mean is usually also known, okay? This means there would be no need to create an interval estimate for it. So like today, we are going to work on finding a confidence interval for the population mean, but this time if sigma is not known, because that's more realistic. That's the type of things that you're actually going to run into. Now let's compare these two formulas that we're going to be talking about. Last class period, we took the sample mean and we add or subtracted the z value times the standard deviation over the square root of my sample size. This was known as my margin of error. This class period, it's literally almost exactly the same thing. But since we don't know sigma, we have to use S, which is the sample standard deviation, okay? We have to use S instead of sigma. The other thing that we have to use here is a T instead of a Z, okay? The T is a new, it's from a new distribution, okay? It's called the T distribution. Now, it's actually formally known as student's T distribution, and let me tell you a little bit about why. The gentleman that created it, I feel bad because I don't actually know his name, he worked for Guinness Beer, okay? And there was a rule in that company that like when you did anything to help them, you could not publish it because it would help their competitor. So this gentleman, he worked for Guinness, and he did a whole bunch of research on like the amount of barley that needed to be used and whatnot, and he created a new distribution. And he realized that this distribution could really help the statistics population, the statistics community. And so he begged his boss and he said, really, I think I need to publish it. Like, my competitors aren't even going to understand what it means and how it's going to help them. And so they finally came to an agreement and they said, yes, you can publish it, but you have to publish it under the name student because, like, we don't want the other people working for us to find out and get really upset about it. So this is, like, his greatest creation in life. And like later it was revealed who he was, but to this day it's known as student's T distribution, so he gets like no recognition for it, okay? Now let's talk about what this T distribution is. The student's T distribution looks like this. As you can see, the T distribution is very much like the normal distribution, like it's very, very similar. It is symmetrically bell-shaped. It has a slightly thicker tail. Like you'll notice here, the red one is the normal distribution, and these two dashed ones are different examples of the T distributions. Now you'll notice it has DF and DF. We're going to talk about that in just a minute. But when the DF, which stands for degrees of freedom, is smaller, the tail is kind of higher off the ground than when the degree of freedom is higher. The higher the degree of freedom, the closer it gets to the normal distribution. So with the T distribution, it has slightly thicker tails, which means there's a little bit more space there. The shape of the T distribution approaches the normal distribution as the degrees of freedom become larger. So the bigger degrees of freedom you have, now, and we're going to find this out, degrees of freedom is linked to the sample size, okay? So in essence, the bigger the sample size, the bigger the degrees of freedom, the closer it's going to be to the normal distribution. The normal distribution has parameters of mu being 0 and my standard deviation of 1. So the mean is 0 and the standard deviation of 1. The T distribution has only one parameter. Like, we're not focused on mu, we're not focused on the standard deviation. The T distribution only has one parameter, and that is the degrees of freedom. Now, I could sit here and go through this entire explanation of what the degrees of freedom came from and how it applies to us, but we really only need to know what it is, okay? The number of degrees of freedom is the number of values from the sample that can vary after imposing restrictions on the data. That's really confusing, but here's what it means. If you have a data set with n equals 5, so a data set sample of 5, then 4 of the data values can vary freely. whereas the fifth one would have to have a particular value in order for the 5 data values to have a specified mean. That means the degrees of freedom is n minus 1. The degrees of freedom is literally just my sample size minus 1. That's all it is. So if you have a sample size of 5, my degrees of freedom is going to be 4. If you have a sample size of 100, my degrees of freedom is going to be 99. That's it. Okay, that's all degrees of freedom is. So let's talk about how to find the area under a t-curve. This is different than a normal distribution. Okay, we are working with t-values instead of z-values. So you need two things in order to find the area under a t-curve. You need degrees of freedom, and you need your alpha over 2, just like we did last time. Okay? Now, to find the area under a t-distribution on Excel, we have this nice little formula. It's equal t dot inv. Notice how that's really similar to norm.s.inv, but this is a t-value, not a z-value. So t dot inv of alpha over 2 and your degrees of freedom. So let's just do some practice with finding t-values here. On number 1, it says find t sub alpha over 2, comma, degrees of freedom of the following combinations of alpha and n. So something you need to know. Sometimes, instead of saying find the t-value or whatever, find the area, they will write it like this. They'll say find t sub alpha over 2, comma, degrees of freedom. They're like reminding you that you need to use your degrees of freedom here. So if my alpha is 0.05, how am I going to find alpha over 2? We're going to divide it by 2. So that's going to equal 0.05 divided by 2. Okay? Now, my sample size is 15. What does that mean my degrees of freedom are? 14. You can put this if you want. You can come over here and put degrees of freedom equals 14. I never do that because, like, I just know that it's one less, and so I do that mental math every time. But you are welcome to do that if you would like. Now, here is how we find the area under a t-distribution. We're going to type in equals t dot inv. And just like we did with the z-value, we need to find the area to the left of it. So, or excuse me, to the right of it. So we need to go 1 minus, and we want that 0.025. 1 minus 0.025. Then we're going to go comma. And my degrees of freedom, if you have the cell reference, you can use it. I always just type it in because we can do that mental math. And you should get 2.14. Okay, let's try it again. On letter B, if my alpha is 0.01, my alpha over 2 is going to equal 0.01 over 2. And then we can come over here and we can type it all in. So t dot inv of 1 minus that 0.005, comma, degrees of freedom. What's my degrees of freedom here? 19. Very good. And we should get 2.86. So try number C on your own, or letter C, sorry. Say that again? Negative? Oh, because you need to go 1 minus. 1 minus. Now, if you'll, Marissa had a really good point. She said she keeps getting negative. Notice like they're the same number. It's just negative instead. That means that you just used the wrong side, so you need to use 1 minus. All right. So finding the t-value, or finding the t-value, guys, really isn't that much different than finding the z-value. That's it, okay? We're still using t dot inv. Now, let's apply it to some problems here. This is confidence interval for my population mean when we don't know sigma. This is more realistic to an actual problem that you would run into in the real world. Again, why would we do all this information for the sample when we know the information already about the population? It makes no sense. So, example 1. The following is a random sample of annual salaries of high school counselors in the United States. Assuming that the distribution of salaries is approximately normal, construct a 90% confidence interval for the mean salary of high school counselors across the United States and interpret the interval. So we don't know the mean salary of high school counselors across the state. We don't know anything about it. We just have this small sample. So that means on that table we would go sigma unknown. And that means we're going to use this little formula right here. Okay, x bar plus or minus t sub alpha over 2, comma, n minus 1. Notice right here, they're literally reminding you about the degrees of freedom. They're reminding you about that. And then multiplying it by the standard deviation over the square root of the population, or sample size. Now, this list of information over here is not necessary. I do it to organize my thoughts. Like, you don't have to have that in order to solve these problems. You don't have to memorize what that stuff is either. I literally just listed out things I knew I would need to put in this formula. For example, in this formula, I know that I need x bar. So I put a line for x bar. I need to find that. I know that I need my t value right here. To find my t value, I need alpha and alpha over 2. So that's where I got this, alpha, alpha over 2, and then I did 1 minus so I could find my t value. All of this right here is what we just did on those examples above. Okay, that's where I'm getting that information. I'm just thinking about what I need. Then I also, based on this problem, know that I need my sample, or excuse me, my sample standard deviation and my sample size. That's where S and N come from. I'm literally just listing out what I need. Then I remember that this is called the margin of error. So after I find each of those individual values, I put a spot to actually find my margin of error. Okay, that's where that list of information comes from. So let's figure it out. How am I going to find my x bar from this problem? Yeah, we're actually going to have to find the average of all of those. So let's type in equals average of, and we're going to have to select all of those salaries. Now, if you'll notice, it comes up as actual numbers because that's the method that I put it in. I made them currency, so like yours is going to come back as a currency. If you're doing this for Hawks and it doesn't, like that's okay. You just got to be smart enough and understand that it's money, okay? Now, how am I going to find my S value? Good. We're going to have to find the standard deviation. So standard deviation dot S or P? S. This is a sample. Very good. And we're going to select it all. And if you'll notice, this one didn't come back as money, and that's okay. That's okay. Okay? Now, N represents my sample size. How many values did they give me in my sample here? 7. So knowing that, can you tell me what's my degrees of freedom? 6. Very good. Now, alpha, who remembers where we find the alpha from? Okay, we look at the confidence interval. The confidence interval is 90%. My alpha, or level of significance, is what's left of that. So if 90%, 0.9 is my confidence interval, what's my alpha? 0.1, very good. Okay, then we're going to take my alpha over 2. And then I'm going to take 1 minus that alpha over 2. Now, to find our t value, it should be a little bit easier because we don't have to do the 1 minus. So let's type it in. T dot INV of that 1 minus alpha over 2, so 0.95, comma, what did we say my degrees of freedom were? 6. Very good. My sample size was 7. My degrees of freedom is 6. Very good. Okay? Okay, so now we have all the little pieces of information that we needed. To find my margin of error, we have to take my t value and multiply it by my sample standard deviation and divide it by the square root of my sample size. Order of operations is going to take care of all of this within Excel, so we can just type it on in. So we're going to go equals t value times standard deviation divided by square root of my sample size. I'm going to let you guys look at that up there before I move on. I've got it all in there. Okay. Now that margin of error is what we're adding and subtracting to create our interval. So to get the lower and upper boundaries, what we're going to have to do, to get the lower ones, we're going to hit equals. And what are we adding and subtracting this margin of error to? Do you guys remember? That's going to be my x bar. So we're going to say equals my x bar minus my margin of error. And look, it puts it in money. That's really nice. And my upper is going to equal my x bar plus my margin of error. And that's going to be my interval. Okay? Now, the last part of this problem said interpret the interval. What that means is we are literally going to write a sentence. We are going to write a sentence so you understand what the heck these numbers mean. This sentence, like as I'm creating these lessons, I've realized this sentence really helps me comprehend what the crap we're finding and like what these numbers really mean. So this problem was talking about high school counselor salaries in the United States, and they wanted a 90% confidence interval. So what we're going to say is we are 90% confident that the mean annual salary of high school counselors in the United States is between $39,978 and $55,922. So we are 90% confident that the mean annual salary of high school counselors in the United States is between $39,978 and $55,922. In layman's terms, they're not paid that much. We okay with that? So is this really that different from what we did last class? Is it really that different from sigma unknown or sigma known? No, the process itself is the same concept. The only difference is we have to use the t-distribution and sample values instead of the z-distribution and population values. So let's try it again on number 2. The attendance records for a random sample of 28 women's basketball games at one university revealed that the mean number of fans at each game was 4,125 with a standard deviation of 741. So this is just a sample. To predict ticket sales for next year, the athletic office needs a confidence interval for attendance at these games. Using a confidence level of 95%, construct and interpret a confidence interval for the mean number of fans at women's basketball games at this university. Assume the population distribution is approximately normal. So we have to assume the population distribution is approximately normal because they only took a sample of 28 games. Okay? We cannot assume, unless they tell us, unless it's over 30. Do you remember that? So since it's under 30, they told us we can assume that it's approximately normal. So here's what we're going to do. I'm going to pause for a minute, and I want you guys to see if you can figure out all of these values. I'm going to come back and show you how to in just a couple of minutes, but I want to give you time to see if you can figure this out on your own. All right, so let's talk about what we got here. So the x bar, the sample mean, they said was 4,125. Oh, no, we don't want to type. Hold on. The sample mean was 4,125. Then it told me that my standard deviation was 741. My in value, they said they took a sample of 28 games. Now my alpha comes from my confidence level. A confidence level of 95% means my alpha is 0.05. Alpha over 2. 1 minus that. And then my t-value. So I'm going to go t dot inv of my 0.975, comma, what's my degrees of freedom going to be here? 27. Very good. 1 lower. Now to find my margin of error, we're just going to take equals my t-value times my S value divided by the square root of n. So t value times S value divided by square root of my n value. Okay, that's my margin of error, t times S divided by radical n. Then we need to add it and subtract it to my x bar to get my lower. So my x bar minus my margin of error and my x bar plus my margin of error. Okay, so my lower is 3837 and my upper is 4412. But we got to talk about what this means. Okay, we are talking about population or attendance at a basketball game. How do you think we should probably round that? Do you think we should round to the nearest tenth? No, what should we round to? The nearest whole number. Like, these are people we're talking about. We should probably be respectful of that and round it to the nearest whole number. All right. Now, let's write a sentence talking about our findings, okay? We are 95% confident, okay, 95% confident that the university can say the mean number of fans at the women's basketball games is between 3,833 and 4,412 people. So we are 95% confident that the university can say the mean number of fans at the women's basketball games is between 3,838 and 4,412 people. Doing okay? Lainey, you good? Cool. Okay. Let's talk about number 3. And the reason we're talking about number 3 is because you're going to see problems like this on your homework, and I want to tell you how to address them. And it says, suppose a 90% confidence interval for a population mean was constructed from a sample, and the resulting interval is given. So the population mean is in between 162 and 198. What's the value of the mean collected, and what was the value of the sample margin of error? So literally, they gave me the interval here. They're saying, okay, my interval is 162 to 198, and my mean is in between them. Where exactly is my mean when I say between them? It's exactly halfway. So to find the mean, you literally have to find the average of these two numbers. So we need to, how do we find the average of two numbers? Add them together and divide by 2. So we're just going to do that in the cell. Now be careful when you do this in the cell, because when you add them together, you need to put them in parentheses. So 162 plus 198 needs to be in parentheses, then divided by 2. So what is the mean here? 180. Well, then it says, what's the value of the sample margin of error? Now remember, the margin of error is like how I'm getting from here to here and how I'm getting from here to here. What am I adding to this and what am I subtracting from this? What do you think we could do to figure that out? Subtract what? Yeah, why don't we just take the big guy, 198, minus the mean that we found, 180. And that means my margin of error is 18. Now, there is another way to find that margin of error, just so you know. Okay, so sometimes they won't ask you to find the mean, they'll only ask you to find the margin of error. To do that, we want to see, like, okay, what's the difference between this 162 and 198? What's the difference between these two numbers? And split the difference. So you could also do that as 198 minus 162 and divide that by 2. Okay, so there's 2 ways that you can do that. In summary, To find this value, you need to find the point estimate. You need to find the right critical t-value using equals t.inv. You need to calculate the margin of error, and then you need to calculate the upper and lower boundaries. Okay? Then write the interpretive sentence. That just helps you understand what the heck is going on. The formula for finding the confidence interval when sigma is unknown is also on your formulas and table card. Be sure to locate it so you know that where it is and you need to use it. I'm supposed to get that back from the copy center today so you guys can have actual physical paper copies. I'll check after we're done here, but we'll see. Okay? Okay. Now, here is that little table that I gave you again. Okay, here's that little flow chart to our thought process, all right? It says finding a confidence interval for the population mean. If the population is normally distributed or your sample is greater than 30, you just have to ask, is sigma known or is sigma unknown? And you have your two formulas that you can use, okay? Now, let's talk about sample size. Okay, let's talk about sample size. What is the minimum sample size you need to achieve estimates with a level of accuracy that is appropriate for making decisions with precision? So sometimes you use samples that are available to you. In this class, I'd be like, okay, I'll just use a sample. But sometimes you need to know if you have the right size of sample. If I wanted some really good data about this class, would it be wise for me to take a sample of 2 people and say that's a good representation of what we got going on here? Probably not. So how do we know what size of sample is appropriate? Okay? So if you pick a sample size that is too small, your data might not have the accuracy that you want. If you pick a sample size that is too big, you might not have the resources to measure it. Okay? So we have to find that sweet spot. If we take the formula for margin of error, okay, if we take the formula for margin of error and solve for n, don't forget, n is your sample size, we have created a formula for determining the appropriate sample size. Now, I thought about it. I could sit here and make you actually do that, give you the formula for margin of error and be like, we need to use some algebra and solve for n, but no, I think we're okay. Let's just look here. If I took my green box above and my purple box above and solved just the margin of error for n, so not the whole thing, not x bar plus or minus, just the margin of error, and solved it for the sample size, here's what I get. If you know sigma, it's going to be z sub alpha over 2 times the standard deviation over my e. What do you think e stands for? Error squared. And purple is the same thing, but instead of standard deviation, that's sigma, we use s. Okay? Now, let's do some examples so you understand what the heck we're talking about. Determine the minimum sample size needed if we wish to be 90% confident that the sample mean is within 2 units of the population mean. An estimate for the population standard deviation of 8.4 is available from a previous study. So my first question to you, do we know our population standard deviation? Do we know sigma? Yes, it says an estimate for the population standard deviation is 8.4 from a previous study. That means in this formula, is sigma known? Yes, we're going to use the green box. Okay, that's the formula that we're going to use. Okay, so I have it here for you. Now, from this information, I was like, okay, z sub alpha over 2. That means I need alpha over 2 to find my z value. It would also help to have my critical level, or my confidence level here. And then E stands for your error. Okay, so let's figure out if we can get all this information. So what is my confidence level here? 90%. So I'm just going to make that a 0.9, which means what is my alpha? 0.1. To get my alpha over 2, divide it by 2. And then to get my z value, what am I typing in? Norm.s.inv. Why am I not using t.inv? Yeah, we're not asking for t, we're asking for z. This is a normal distribution. Norm.s.inv of 1 minus 0.05. Now this E, this error, is kind of tricky. You have to pay very close attention to what they're asking in the problem. Determine the minimum sample size needed if we wish to be 90% confident that the sample mean is within 2 units of the population mean. That means if I have the population mean here, okay, and I have boom and boom, they want 2 units. So I want plus 2 units and minus 2 units. That right there is the margin of error, otherwise known as your error. So my error here is 2 units. And then what did they say my sigma was again? 8.4, very good. Now, we need to think about how we're going to put this into our Excel cell, because we have some multiplication, division, and squaring. So inside of my parentheses, I'm going to have my z-value times my sigma divided by e. That's okay. Order of operations will definitely handle that. But on the outside, I have the whole thing squared. So if you want, you can do this in a cell and then take your previous answer and square it. Or if you're thinking ahead, you can start it off with a parenthesis, end it with a parenthesis, and square the whole thing. Okay? So I like to do it all at once. It just makes more sense for me. So I'm going to type in equals, open parenthesis. Then we're going to go z-value times sigma divided by my error. Close your parenthesis and square it. Now, be careful, because you get 47.7, but we are talking about a sample size. So yes, my in value that I got is 47.7, but that's not an okay sample size, which means we have to figure out what is the actual sample size based on this result. If I get a sample of 47, is that going to be enough? No, we always need to round it up. My minimum sample size here is going to be 48. We always need to round it up. Even if it's like 23.01, your answer should always be rounded up. All right, let's go to number 2. For a psychology experiment, Emma is assigned the task of finding the mean number of hours of students' sleep per night. Her results must be at a 99% level of confidence with a maximum error of 0.25 hours. Assuming the standard deviation is 1.4 hours, how many students must Emma survey? So do we know the sigma? Yes, so again, we're going to use that same formula. Okay? So help me out. What's my confidence level here? 0.99, which means my alpha is good, which means my alpha over 2 is very good. Let's find my z-value. Norm.s.ind of 1 minus 0.005. What did they say my error was here? 0.25, very good. And what about my standard deviation? 1.4. Now if you'll notice I accidentally put S here. That should not be S, that should be sigma, because they did tell me. Now let's find my n values. Again, we want to start it off with an open parenthesis. Then we're going to take z times sigma divided by error, close that puppy, and square the whole thing. Ooh, this is a really good example. We have 208.07, which means my minimum sample size should be 209. We always have to round up. Always need to round up. In summary, if we are willing to increase my margin of error, like if we're willing to increase how much error I want, then we can decrease the sample size needed. Okay, if you're okay with a little bit of error, you can use a smaller sample size. However, the more confidence we want in the interval, the larger the sample size must be. If we are only willing to accept a small margin of error, then we need to be okay with having a larger sample size. All right? Now, below here, I have those steps just like we have in the past. Find the right critical value, calculate your N value, and round up. The formula will also be on your formula sheet that I'm going to give you in just a minute. So on your Hawks homework today, you are going to do homework 10.2. Be aware, homework 10.2 is a mix of what we did this class and last class. You have to read very carefully to know if sigma is known or sigma is unknown. Okay, so keep this practice up, and what I would do is I would maybe scroll up to this table right here so you have both formulas readily available, or write them down in your notebook so they're right there. If sigma is known, you can use the z value. If sigma is not known, you have to use the t value. Okay, get to it.